Welcome to this lecture series in real analysis. Last time we looked at an ordering on the rationals, which is same as the ordering that we are familiar with from high school. So let us recall what we know so far, and in this lecture we will be learning about a defect in rational numbers, which is the reason why we need to go to real numbers to develop calculus. So we need to know what are posets. Posets stand for partially ordered sets. Formally, it's a set P equipped with a certain relation, which is reflexive, antisymmetric, and transitive. Then we looked at what are rational numbers. We defined them as equivalence classes of under a certain equivalence relation on a certain set, which was the set of all pairs A comma B, where A and B are integers, but B is non-zero. And then we defined an equivalence relation on it in a certain way, and then the set of all the equivalence classes was defined as the set of all the rational numbers. And last time we looked at an ordering on this, which was defined by the following recipe. So if we have alpha and beta 2 rationals, then we can write alpha as A by B for some B positive, where A is an integer, B is an integer, and B is a positive integer. Similarly, beta can be written as X by Y, where X and Y are integers and Y is a positive integer. And then we define alpha less than equal to beta if this happens. And I forgot to mention the well-definedness of this. One has to establish the well-definedness simply because we are defining something via representatives. So we defined alpha less than equal to beta by choosing representatives for alpha and beta, and then the condition had to do with representatives. So one has to establish well-definedness, but that is very easy, so I leave that out. Okay. Here is one problem which is very important for this lecture, which is why I have marked it with dagger. Actually, I should mark it with star because it is important to follow this lecture. It's a very standard problem. We want to show that there is no rational number r whose square is 2. So this you can find anywhere. If you just Google, you can easily find it, but I encourage you to think about it if you have never seen it before. All right. And yeah, so when we say r square equals 2, here 2 stands for the rational number 2 by 1. So that's what 2 means. Okay. Right, so first we will discuss what is an upper bound to a subset of a poset. So fix a poset and fix a non-empty subset of the poset. Then we say that an element little p is an upper bound of S if, well, let me write this as maybe X. So we say that X is an upper bound of the set S if X dominates every element of S. It's a very natural definition. Basically, it is sitting above everything in S in some sense. Okay, so let's look at examples to understand this better. Consider this poset, the set of natural numbers with the usual ordering. So that is our poset. And this is our subset, the first 3 natural numbers. Then we can write down many upper bounds to this. So one such upper bound is 3. 3 itself is an upper bound to S because it is dominating everything here. Note that we do not have a strict inequality here. So 3 is an upper bound, and 4 is an upper bound, 5, and so on. All of these are upper bounds to S. Okay. Next time, in the next example, we have the set of all the primes as the set S, and our poset is the same. It is the set of natural numbers with the usual ordering. Then S does not have an upper bound. And the reason is number theoretic. Basically, first one needs to recall that there are infinitely many primes. And it follows that for any natural number n, there is a prime bigger than it. And therefore, there cannot be anything in the set of natural numbers that upper bounds everything here. So it is not, S does not have an upper bound in n. It is important to mention the poset we are working with. So the set S does not have an upper bound in the natural numbers. So this says that, this shows that upper bounds may not exist. They may not always exist. Okay. Now we have the example of the Boolean poset. So this is the power set of the first three, or rather, power set of 1, 2, 3. So that's that, and the poset relation is via inclusion. So this is dominated by that because this is contained in that, and so on. So here, if you pick something, let's pick maybe these three elements. So that is our set S. Then this serves as an upper bound of this set, or that serves as an upper bound. So I leave you to figure that out, what I just said. Let's move on. Now for the most important thing, least upper bound. Fix a poset and fix a non-empty set. Then an element X in the poset is called right now it's a least upper bound of S if X is an upper bound of S and whenever Y is an upper bound of S, we have X is at most Y. So I'm reading this as X is at most Y. Right, so what is it trying to say? So something is a least upper bound of S if first of all it is an upper bound and it is smaller than every other upper bound, and hence it is true to the phraseology. The phraseology is well chosen. It is the smallest of all upper bounds. Okay, so the definition is simple, but let us note one thing before we move on. Least upper bounds are unique if they exist. So this LUB, least upper bound, can be abbreviated as LUB. So least upper bound is unique if it exists. The reason is very simple. So say X and X prime are least upper bounds of a set S. Then by definition, this happens. Why does this happen? This is a least upper bound while this is for the moment just some upper bound, and hence we have this inequality by definition of a least upper bound, and for the same reason we have the reverse inequality, and these two imply that X equals X prime, and hence we cannot have two distinct least upper bounds. Alright, so now finally we will show that there is an undesirable feature sitting in Q, which is the incompleteness of Q, or more informally, there are gaps in the set of rational numbers, which is why we need to invent something more complicated, namely the set of real numbers. Okay, so consider the poset Q with this ordering that we discussed last time. We also noted that it is a total order, meaning any two distinct elements in Q are comparable, meaning either one is smaller than the other or the other is smaller than the one. Okay. Define S as all those rational numbers which are positive and whose square is less than 2. So this is a set, and this is a non-empty set because, for instance, 1, the rational number 1, which formally is actually 1 by 1. So the rational number 1 satisfies this. So this is a non-empty set, and it has an upper bound, namely 2. So the rational number 2, which again is 2 by 1 formally. So 2 is an upper bound of this, because if R is a positive rational whose square is at most 2, then R is also at most 2, because if R were greater than 2, then its square would be at least 4, and this wouldn't be true. So this has an upper bound, and one such upper bound is 2. We claim that S does not have a least upper bound. And this is the defect. There is a set with an upper bound, but not with any least upper bound. This seems like there is a hole left in the rational numbers. Okay, so we will be proving this. So assume on the contrary that we have a least upper bound, call it M, and we want to come to a contradiction. So we will be discussing three cases. Case 1 is that M square is less than 2. Okay. So in this case, let or say, since M is a rational number, we can write M as A by B, where A and B are integers and both are positive. Why is that? Because M is after all a positive rational. Being an upper bound to a set which contains only positive things, M itself is positive, and hence you can write it as A by B, where both A and B are positive. Okay, and say at the same time, say 2 minus M square, which is a positive rational because of this assumption. This is C by D, where C and D are positive integers. Okay, now for any natural number, we have this is equal to that, and hence so far we have done just some mindless algebra. The point is, what we will end up doing is that we will show that there is some n large enough such that this is positive, and hence we would conclude that this guy is lying in the set S, and since M was an upper bound to S, M would dominate this, but that is of course a contradiction. So that will be the problem. Okay. So we'll do everything in detail, but this was the outline. So what we have is, we will write for 2 minus M square, we'll write C by D, and for M we'll write A by B. So what we get is 2 minus that is equal to 2A by B times N. And now, since N could have been chosen to be any natural number, set N as equal to that. This is a choice that was, in retrospect, this has come about. It's not like I just came up with it out of nowhere. One just had to choose some large enough N, and this is convenient. Okay. So then, this is equal to right, which is equal to C by D minus okay, I've done just some basic algebra. This is strictly greater than. Why is that? Because A and D are positive integers, so this thing is strictly less than that. And hence, since there's a minus sign here, we get a strictly greater inequality. But what this is equal to that thing, and therefore, with this value of N, call it N naught. So therefore, this is greater than 0, because this is at least 0. C is after all a positive integer, so this is at least 0. D is also a positive integer. So this thing is strictly greater than 0 because there's a strict inequality appearing along the way. So this is strictly greater than 0, which implies that m plus 1 by n naught whole square is less than 2, which implies this guy is in S, but since m is an upper bound to S, we have this, which is a contradiction. This is a contradiction. So in this case, we did not even need to use the fact that m is the least upper bound. We just needed to use the fact that m is an upper bound and that it lies in S, meaning it satisfies this inequality. So that's all that we needed. Okay, so case 1 gives a contradiction. Case 2 is equal to that. So this is certainly not possible because m is a rational number. So this is already a contradiction if you had solved the exercise that was mentioned in the beginning. So case 2 is anyway not possible. Case 3, which is the last possible case. So in this case, what will happen is that by the same kind of reasoning, here we can find a natural number n such that this will remain to be true. Therefore, this will be an upper bound to S. Right? And since m is the least upper bound of S, we have, which is a contradiction. So in any case, we have a contradiction, and therefore there is no least upper bound to the set S that we have. Right? And this should feel like an incompleteness, a defect in rationals, and hence we will ask the question, can we find a better system of numbers or a bigger system of numbers where this defect doesn't appear? And that will occupy us for a few lectures. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.